Good afternoon, everyone. My name is Chad Welber with PCB Piezotronics. I work in the research and development area here, and today I'm here to talk to you about microphone calibration. So, what is calibration, and what does it mean to be calibrated? Why do we calibrate? What do we at PCB as a manufacturer do for calibration? And what should you in the field do when you're using your microphones and you want to perform a calibration before and hopefully after your test? So just to kind of do a quick outline here, what is calibration? It is a method of verifying the amplitude response and system linearity over the intended range of use for your microphone. It provides a physical meaning to an electrical output. The units of transduction for a microphone are millivolts per Pascal, but what that means is the microphone itself is outputting in volts or millivolts, and it is directly related to pascals or pressure at the input terminal of the microphone. For microphones, a typical manufacturing calibration includes an open circuit sensitivity, meaning for the cartridge, what is the sensitivity of that cartridge just on its own? What it also includes either the free field response of that microphone, meaning what does that microphone do in a free field, or the pressure response of the microphone, meaning what does that microphone do when used in a coupler or mounted flush to a wall. As you see by the asterisks, in many cases, these two responses are developed and corrected from an electrostatic actuator response. And I'll talk about that a little bit later on in the presentation. So why do we calibrate things? Well, the obvious reason is to make sure that the performance of the sensor is according to its specification, and to make sure that we collect meaningful data. Comparing volts to volts to volts to volts when it has no meaning behind it, meaning you have, okay, I've got a microphone that's outputting 1 volt, but I don't know what the sound pressure that's equivalent to on the other terminal is. What that also means is that another reason to calibrate is to make sure that your sensor remains healthy. So why recalibrate? Making sure that that sensor doesn't shift over time. An example of a very stable sensor in most cases is a measuring tape. The length of the tape does change with temperature, but for the most part, the marks and points on that measurement tape over time aren't going to move. Sorry, I had to double check and mute somebody here. And it's often required that you do recalibrations for your systems by either ISO 9000 or contractual reasons or some other quality system that you may be working with. And at the end of the day, what is decision for not only why you should recalibrate, but how often, and it's a risk versus reward thing. If you take 3 months worth of data, 3 years worth of data, and you don't do a recalibration or a calibration check, and somebody calls into question your data to show, hey, this isn't the actual correct value that you measured here, what does that mean for the quality of all your measurements up to that point since your last calibration? So calibration and your calibration interval are definitely a risk versus reward thing. Standards. So everything I'm going to talk about in this presentation is a very standardized process. To start out, ISO 9001, which is a company quality management system. That basically is the guideline by which individual companies and corporations and even small companies of a few people should go by to say, okay, I do things the same way over and over to make sure that I maintain a quality standard by which my product is put out there. Furthermore, because we're talking about calibration, because we're talking about measurement devices, ISO 17025 for calibration laboratories is another standard that needs to be followed. And what that goes through is the general requirements of the competence of a calibration laboratory, and specifically it has to be accredited by either A2LA, NABLAB, A-Class, depending on where you are in the world. One of these accreditation bodies has to come in and make sure that you're following the rules and standards of ISO 17025 if you're a calibration laboratory. Furthermore, specifically for microphones, there is a series of standards that is carried internationally called the IEC 61094 series of microphone standards. These standards outline not just the calibration methods of microphones, but some of the factors of their construction for measurement microphones. These standards are being refined and worked with even in the current date. So when you go and look at these standards, they are up to date and they are still active standards. The reason we use these standards is so that everywhere around the world, whether I'm taking a measurement here in Buffalo, New York, or someone in the chat is taking a measurement in Stevens Point, Wisconsin, or there's somebody in Australia taking a measurement, we can all compare notes on the same thing that we're measuring. And in order to do that, we have to have a way of tracing our measurement back to some standard, something that says this is the conversion from a Pascal to a volt. And in many cases, what we use is a chain, a traceability chain, where we'll generate a reference via primary calibration with a laboratory standard microphone. From there, we will do comparison calibrations from the laboratory standard to reference microphones to the measurement microphone that you'll use in the field. And it's very important to note that whatever laboratory you're using must have some reference or some way to get a reference back to a laboratory standard or to primary calibration. Otherwise, you don't know the accuracy of your measurements or of your calibrations from that laboratory. And again, this is just fundamentally going through, but then applying the standards to it. So first, we start with the base units of the metric system, and in order to get from those base units into a microphone calibration, we do a primary calibration by pressure or free field reciprocity. That creates an artifact called a laboratory standard microphone. And from there, the laboratory standard microphone can be used either via primary calibration or also a pressure comparison or a free field comparison calibration in order to create a reference microphone. In our factory here, we have both laboratory standard microphones and reference microphones. And then what I do is I'll use the laboratory standards as a measurement check on our reference microphones. And then in production, our reference microphones are used as single point pressure calibration for our measurement microphones. And furthermore, we use an electrostatic actuator in production for most of our microphone models with an electrostatic actuator in order to generate our frequency responses. So I'll talk about kind of a method of calibration that is both we use this here in the factory, and this is something that many of you should be using in the field when you're performing measurements before and after your measurements, and that is a pressure calibration with a sound source or a calibrator. And the method and the components or the ingredients of this calibration are your sound calibrator, a microphone on a chest that you want to be calibrated, and in the case of all measurement microphones, it either has an integrated preamplifier, or if you have a setup where you have multiple cartridges that use the same preamplifier you will use a separate preamplifier. Before you go out in the field and you start doing noise measurements, and This says field calibration notes. It should say things to know about calibrating when you're about to do field measurements. The first thing is make sure you have a good sound calibrator traceable to IEC 60942. Make sure it's within its calibration cycle. Make sure you have spare batteries for it and all the required adapters. Meaning if you've got quarter-inch microphones, make sure you've got the quarter-inch adapters for those microphones. Have an understanding of how the calibrator works and read the manual if you need to, especially for things like signal settling time and the amount of time before that the microphone needs to be inserted into the calibrator before you can actually take a measurement. Once you are in the field and preparing to do the calibration, make sure that all of the equipment that you have is acclimated to your environment. Microphones are very sensitive to temperature, humidity, and ambient pressure change. All three of these factors will have a determination of what the sensitivity of the microphone is. Also your calibrator, make sure it's at the same temperature, humidity, and ambient pressure, because if you take a microphone that's at one temperature and a calibrator that's at a different temperature and put them together, you're going to have some weird results because the calibrator will be trying to make the microphone its temperature and vice versa. And then once you're getting ready to calibrate, get your test basically set up. Exact cables, data acquisition channels, signal conditioners. Have it all set up so that you're not just calibrating your microphone, but you're calibrating your entire measurement chain. When you're calibrating, and this slide is meant to almost be like a pocket note of all the things you need to do when you're going to do a microphone calibration in the field. Make sure your DAC channel and signal conditioner are turned on properly. Make sure they're set to the right settings and they have them set to the gains that you actually want things to be. And the next step is insert the microphone into the calibrator and allow it to get used to being under pressure in the calibrator for 30 seconds. Don't handle the microphone with bare hands because the temperature of your hands will have an effect on the microphone output. And the sealed cavity of the calibrator induces an ambient pressure change that needs to equalize around the microphone. It's a note here, I've had this question before. Can you damage a microphone by putting it into a sound calibrator? And my answer is, if the sound calibrator is designed well, no. I've never heard of any of the mainstream models of sound calibrators damaging a microphone just by inserting it. They should have enough of a leak path and enough volume on the inside that it won't damage or destroy the diaphragm of the microphone. Once the microphone has been inserted in the calibrator for 30 seconds, turn on the calibration and wait for the stabilization time. Again, see the manual for that. Take a reading with your DAC or your calibration software and verify the overall system sensitivity. If it's a big change since the last time you did a measurement with this setup, check it again just to verify it, because your last time you did a test like this, you may have been testing in very cold temperatures and you may now be testing in very hot temperatures, and you may have 1/10 to 2/10 to 3/10 of a dB of change. And that's an important thing to take note of over the course of your measurement history. So again, we're just going to go through this again with the kind of the graphics in here. So, and it kind of, these graphics will outline a little bit of what goes on inside the mathematics and mathemagics of how to do a calibration. You have a sound source that creates a pressure, a known pressure. We usually look at these numbers in decibels, but these also are equally as valid in pascals and volts. You have a preamplifier output voltage. And if you don't care about anything other than that system voltage with that microphone, with that preamplifier, the sensitivity of the microphone preamplifier system is the voltage output of the preamplifier divided by the pressure input of the sound calibrator. Now, because we build microphones here at PCB, we sell both microphone cartridges and we sell microphone systems. When you're dealing with what a microphone cartridge is, independent of a preamplifier, there's a second step that needs to be done. And the reason for this is the microphone once you put it onto a preamplifier, the preamplifier has a small gain on it that changes the output of the entire system. And it's important to know, because if you take that microphone and put it on different preamplifiers, the gain of different preamplifiers may be a little bit different. So what we do is we will actually take the microphone, and we have a special preamplifier that we can use called an insert voltage preamplifier. And what that does is it allows us to apply a voltage to the electrical terminals of the microphone and then measure the output of that preamplifier due to that input. And once we have it matched, the output to the input of the previous measurement, we can calculate out the open circuit sensitivity of the microphone. To go over this once again is we apply an insert voltage to the ground terminal of the microphone, and we measure the output voltage of the preamplifier. And we keep adjusting the insert voltage across the microphone terminals until the output voltage of the preamplifier is the same as VP from the previous step, meaning it's the same voltage as the output of the preamplifier in this setup is the same as the output in the previous setup, where the input was excited by a pressure. And with that, we take the input voltage, or the insert voltage, and divide it by the pressure from the previous setup, and that gives us our open circuit sensitivity. I apologize if that was very confusing, but it's basically a setup to say we're taking the preamplifier system out of the equation and saying this is what the microphone's sensitivity is independent of a preamplifier. As I said, open circuit sensitivity is a property of the microphone, independent from the preamplifier. If you're buying just a cartridge from us, it's measured typically at a single frequency, 250 hertz. We give it to you in millivolts per Pascal, and we'll also give you sensitivity level in dB, which is dB with reference to 1 volt per Pascal. The broadband frequency response of a microphone is measured using an electrostatic actuator by the manufacturer, and then we correct that to free field. There are a couple models of microphone that we make where we do straight up free field or straight up pressure calibrations, but for the most part, when we're talking about precision condenser microphones, you're talking about a corrected response from an electrostatic actuator. So now I'd like to talk a little bit about calibrator types. The first kind is piston phones, and piston phones are typically open loop systems that have very constant and well-known volume with respect to a volume velocity change that is going on within the system. Literally, most piston phones are two pistons that are going in and out as being forced by a cam. If you look at the drawings that I have to the right here, you can see I have two little pistons on either side of this cam piece here. And that cam rotates in such a way that those pistons go in and out. And this metal hoop here, or this black hoop here, is a spring that holds the pistons in. The blue part is a motor. And from there, the pistons are literally changing the volume of this entire area of the piston phone. A piston phone generates a volume velocity, a known volume velocity, which needs to be converted into a sound pressure because that's what a microphone measures. So in order to do that, you need multiple pieces of information. You need to know what the coupling volume is, which is the volume in front of the microphone that's part of not only the grid cap, but also the whole adapter piece that goes with the microphone. It also needs to be known what the adapter is, and it also needs to be known what the microphone size is. And then from there, the volume velocity, because it's an air volume, in order to convert from volume velocity to pressure, you have to know the temperature, humidity, ambient pressure in order to be able to do this calibration. Furthermore, because these parts are all being pushed into a cavity, alignment of all these parts is very important. So if you place this on a table and the preamplifier end of the preamplifier is tipped down and laying on the table, while the rest of the microphone is suspended and up inside here, this volume is no longer constant, or at least not what it should be with everything pushed in and flat against one another. So doing a calibration with a piston phone can be a bit of a challenge, simply because of all the information that you need to know in order to be able to do the calibration. On the other hand, a basic speakerphone calibrator tends to be controlled with a feedback loop. Several systems out there simply have large enough volumes that they are not sensitive to any change in volume. Most times, this is considered a secondary calibration, traceable to a laboratory standard microphone. However, a sound speakerphone calibrator has a known sound pressure. You don't have to do any conversions with it after you're done doing your measurements. You know what the sound pressure is. I don't have to tell you what the ambient pressure or temperature of the environment was in order for you to complete your calibration. I spoke about an electrostatic actuator before, and just here I want to go over what it does. And it literally, I'm very fond of this term, in that it is, an electrostatic actuator is a dumb piece of metal. It has no components other than a piece of metal and some insulative feet. And those feet that you can see in this drawing here are these little tiny parts here that are separating the metal actuator from the microphone, so it can't complete the circuit. And so that there's holes that are perforating this here, and there's a gap here. And we put a strong electric field across here that we are using to simulate a sound pressure. And we go across multiple frequencies, and we will sweep through the entire frequency band that we are interested in for the microphone, and use that to get out what we call an electrostatic actuator response. From there, we will, using known measurements from previously done testing, we will take that electrostatic actuator measurement and apply a correction to give you either the free field, random incident, or pressure response of your microphone. And even further from there, we can give you the responses with respect to a free field with a windscreen, various angles of incidence, various other adapters like nose cones. And we have many of these plotted already. Some of them we are still working on, so with some of our more obscure microphones. But for the most part, everything with frequency response in a microphone is done like this. I have another presentation where I go into how frequency response is done with a microphone acoustically, which if I get any demand for that, please contact sales@pcb.com if you're interested in me giving that presentation later on this year. But this is how you get the frequency response of an acoustic microphone. So the interesting thing with this is, okay, I'm giving you a relative response of the electrostatic actuator, but relative to what? Well, remember, we calibrate our microphones with a calibration source of 250 hertz. So the frequency output of the electrostatic actuator at 250 hertz is set to 0, and then everything else is set to with respect to that. So again, you get your free field, your random incidence, and your pressure response are corrected based on the model of microphone and previous testing. And you can see the pictures down below, a couple of electrostatic actuators, and an image of how the actuator is installed on a half-inch microphone. This large one here is a 1-inch electrostatic for a 1-inch microphone. And again, here are the responses. This is the microphone response for a free field microphone, and the reason I know that is because the flattest response of all of these curves is the free field response. The measured response here is the blue line down at this point. The red line here, I don't know how well anyone can see colors depending on their screens, is corrected from electrostatic actuator to pressure. and the purple line is corrected from electrostatic actuator to random incident. So the last thing I want to cover today in today's presentation are care and handling do's and do nots. The first thing, always store your microphones in a clean and a dry place. Do not leave your microphones out in an engine test cell when not in use to gather dust and fumes. And I do have to note, before I go further on this list, that the only reason any of the do nots are on the list is because they actually happened. Do, tighten microphones to the preamplifier hand tight. Do not use vice grips to make sure that your microphone is secure. Furthermore, don't use vice grips to remove grid caps. We have had several people attempt that as well. Do use an air bulb to gently blow contaminants off the diaphragm. Be very gentle with the diaphragm of a condenser microphone. It's very delicate. It's just to give a reference, aluminum foil that you use for cooking at home, standard aluminum foil, is 8 times thicker than the diaphragm that's on a standard condenser microphone. And you know how easy it is to wrinkle aluminum foil when you're trying to bake some ribs or something delicious like that. Do not use shop air at 100 psi to clean contaminants off your microphone, because you will just end up with the diaphragm blowing in the wind. Do refrain from touching the diaphragm. I know it's a bright, shiny piece of metal, and it's very tempting to just push the big red button. But do not press the diaphragm on it like it's a fingerprint analyzer on the iPhone. Please do leave the grid cap on when you're testing. Unless leave the grid cap on underneath the windscreen. If you're using something like a nose cone, obviously you're taking the grid cap off. When you do take the grid cap off, please be sitting down at a bench so you don't accidentally drop your microphone on the floor and then you have to worry about, well, is it in calibration? Does it still work? Am I going to puncture the diaphragm with a piece of dirt that's on the floor? Oops. Do not discharge the grid cap and leave the diaphragm exposed. In most cases, and in fact, in most cases, the microphone response is designed with the grid cap on. So you're better off leaving the grid cap on throughout all of your measurements. Please be careful whenever you're handling your microphones. I've heard of people dropping them. I've heard people getting them soaked in a puddle in bad weather. Please do not drop microphones into a paint shaker. It wasn't exactly a paint shaker, but it basically, at the end of the day, that's what ended up happening, is they ended up going through a tumbler, and yeah, there wasn't much left of the microphones at the end of the day. Thank you for listening to me this afternoon. Let me look in the chat here quick and see if there's any questions. Don't see any questions in chat right now. I will hold on for a couple minutes just in case somebody has some questions. Please shoot them either to myself or to Jennifer Carlo, and I'll get to them here in a minute. So I do have a question here, calibrating audiometers. Do you need to correct for temperature, humidity, and barometric pressure? I would say it depends on your calibration method. If you're just using, I'm assuming you're saying calibrating the audiometer, not calibrating the microphone. Is that correct, Dave? Okay. I don't know what the audiometer standards call for. I believe the last time I read them, you had to, when you performed your calibration, you had to take note of all of that, but you did not have to correct for all of that. Now, I will say this at this point, for calibrating other apparatus, please, 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 please check with your specific standards. If you're being held responsible for calibrating something, that is completely up to you to make sure that you're calibrating it right. So I always tell people and highly recommend that they own the standards to which they should be calibrating stuff by. We own here at PCB all the standards with which I use to calibrate. And I actually sit on the standards committees also for microphone calibration. So I basically have an open book to all that information. If there are no further questions today, but if you come up with a question, okay, we got one more. Does this work? Oh, I think I understand the question as it's coming in pieces. So I don't have it in this presentation. I have a basic microphones presentation. A lot of people will ask me, can I use XYZ microphone for both free field and pressure and random incidents? And I have 3 basic rules when it comes to that. First rule is, what frequency range are you actually interested in? Because depending on the type of microphone, if it's half-inch microphone, everything below about half to 3/4 of the resonance is a flat frequency response, meaning it doesn't matter if it's a free field, pressure, or random incidence response, they're all the same right up until about 5 or 6 kilohertz. Furthermore, if you want to use the entire frequency range of the microphone, understand that the field type that you're in will be different than possibly the calibration of your microphone, and be ready to calibrate or correct for it in your post analysis of your data. So if you know that it's going to be a couple dB off at the higher frequency, understand that you have to correct for that in your data. And the last thing I tell people is, if you can adjust the directionality of the microphone so that it has a flat frequency response for how you're measuring the apparatus, you can do that. And there's ways of doing that are outlined in ISO standards that talk about, okay, if you have a free field microphone and you're trying to do a random incidence test, you have to angle the microphone in this direction with respect to the source. Usually it's about a 70-degree angle with respect to whatever your source is. Don't quote me on that, because that's from a 25-year-old standard. But for the most part, if you've been measuring things the same way for a long time, I would not change microphones or change microphone styles. I would make sure that all of your measurements are consistent rather than change to make it so that you're using the right microphone to do measurements with. And with that, I will close out today. My email is up there if you have questions, cwalder@pcb.com. There's one more in the acoustic series this year. I believe it's Sound Power Basics is next month, exactly 28 days from today. Same time, same station. So thank you, everyone. I hope you all have a wonderful day and a wonderful weekend. Thank you. Bye-bye.